So welcome to everyone. So topic is a design of beam. T-beam is a RCC beam where slab and beam are cast monolithically and the scale is always under compression zone of beam such that the slab behaves uh, like compression zone of the beam called flange beam. Due to the presence of slab in compression zone, the concrete of the slab is good in compression, contributing compression zone for beam, and hence extra concrete is not required for the beam in compression, resulting in smaller depth of the beam. So next one, so the T beam is the most economical RC beam generally used in frame construction, being a slab combined, but if the slab comes under the tension zone of the beam, then the slab consisting concrete does not take tension and the beam is designed as rectangular beam only where separate concrete is required for compression zone, resulting the greater depth of the beam. So it is an important part of the design of beam. So the stress distribution, bending compression or flexural compression along the total width of the flange is not uniform. Therefore, it is difficult to analyze a T-beam. The total width of flange of the T-beam is reduced to have uniform stress distribution called effective width of the flange. In the case of the total width of the flange of the maximum bending compressive stress takes place at the beam section at half of the width of the beam and the stress goes on decreasing towards end of the total flange. This phenomenon is called shear lag. Next one is that to have uniform bending compression stress distribution along the width of the flange, the effective width of the flange is only used. Thus, the effective width of the flange is defined as an hypothetical flange having uniform bending compressive stress distribution of maximum value such that the compressive force developed in the case of total width of the flange is equal to the compressive force developed in the effective width of the flange. So, in the case of a continuous beam, the beam is designed as T-beam under sagging bending moment nearby midspan where the flange is under compression, but at the support, the beam is designed as a rectangular beam due to hogging bending moment where tension takes place in the slab which cannot behave like flange. So these are the stress distribution of T-beam. So the, where at the top of the portion the maximum stress will be developed and the actual compression bending distribution will be developed in this portion like this. So this one is the depth of the flange and then this one is the flange and then web. So these are the some pictorial example of T-beam. So and also stress distribution diagram with various loading. So like point load, UDL load, like that. So by IS 456 2000, so effective width of the flange as per code book for effective width of the flange first condition for more than T beam that means BF divided by LO divided by 6 BW plus 6 into DW. So less than or equal to S1 by 2 plus S2 by 2. So or B. So these are the some formulas for using T beam, L beam. So T beam, single T beam, and then single L beam like that. So in this note, according to IS 456 2000, if the main reinforcement of the slab is parallel to the beam and transverse reinforcement shall be provided in the flange. Such reinforcement shall not be less than 60% of the main reinforcement at midspan of the slab. The placement of the traverse steel shall be more than or equal to 1 by 4th of the span of the beam slab. So, or either side of the web. So, so this is the span of the slab, and then beam is connected in between the slab, and then mid slab value is AS, that is area of steel. So next one is bars, bars in flange and termed as a rectangular beam. So there are so many types of beams there. So T beam and rectangular beam, and so these are the flexural arrangement of the beam. So in this case, we have to analyze the L beam of the T of the beam is subjected to. So first one is a longitudinal bending moment as usual. Second one is shear force as usual, and then torsion. So this is the most important condition. We have to analyze these conditions. So according to IS 456, the L beam shall be designed or equivalent bending moment combination of longitudinal and torsion. So that is ME1 equal to M plus MT. So M is nothing but a longitudinal bending moment. MT is equivalent bending moment due to torsion. So where D is overall depth of the beam and B is breadth of the beam. So next one is, for example, heavy torsion steel must be at the top. Light torsion steel was not needed at the top. So next we have to see some problem. So I have to read out the problem. So an isolated T beam has the total width of the an isolated T beam has the total width of the total width is 2000 mm and effective span is 6 meter. Thickness of the slab is 150 mm and the breadth of the web is 300 mm. So the overall depth of the beam is 500 mm. There are four bars of 20 dia in tension zone. We have to determine the depth of the neutral axis and the type of a section. Ultimate moment of resistance. Use M20 concrete and Fu for the steel. Use effective cover is 40 mm. So first we have to find out the breadth of the flange. It's nothing but the formula is BF equal to BW plus LO divided by LO divided by B plus 0. So already we know that BW is nothing but 300, LO is 6,000, and then breadth is 2,000. In this case, we have simplified into BF equal to 1157.14. So that is less than or equal to 2000 mm. Hence, it is satisfied. So next one is the 0.36 FCK B into XU, that is equal to 0.87 FOAST 0.36 into 20, 1157.14 XU, that is equal to 0.87415, 4 into pi by 4, 20 square. So XU is nothing but 54.45 mm. So next we know that XU divided by D value. So XU divided by D is nothing but XU value is 54.45, and then 500 D is nothing but 500 minus of cover. So effective depth is 500 minus D. So the cover value already given the question. So finally XU divided by D is 0.11 by 0.1183. So for Fu41 steel, XU limit divided by D is nothing but 0.48. So therefore XU less than or equal to XU limit. So we know that XU value are less than or equal to XU limit value. Hence, the section is under reinforcement. So next one is moment of reinforcement formula is MR equal to FT into Z. So FT is nothing but 0.87 FI EST D minus 0.42 XU. So 0.487 FI is nothing but 415. Area of steel is already, we know that if they are given the value, area of steel is 4 bars of 20 mm dia. So we have to multiply into and simplify the value of 1256.63 value, and D is nothing, effective depth is 460, and the minus of 0.42 into XU is nothing but 54.45. So finally moment of resistance is equal to 198.3 kN. So in this problem, we have to find out the depth of the neutral axis and the type of the section, ultimate moment of resistance. So all the three values we have to find, we already find out. So we are moving into next problem, and then the next problem is determine the moment of resistance of T beam having the following data. So the data are BF equal to breadth of the flange equal to 740 mm, and depth equal to depth is nothing but 400 mm, and BW breadth of the web is nothing but 240 mm, and AST is nothing but six numbers of 22 mm dia bar, mild steel bar, and depth of the flange is nothing but 80 mm. Use M20 concrete. So 0.36 FCK B into XU equal to 0.87 FY AST. So 0.36 into FCK is nothing but 20, and B is nothing but 740. XU is the unknown value, and that is equal to 0.87 FIS 250, and AST equal to FIS 250 because of the it is having a mild steel. So AST is nothing but 6 into pi by 4 22 the whole square. So finally the XU value is 93.11 mm. It is greater than or equal to depth of the flange. So neutral axis lies outside of the flange. Hence, assumption is wrong. So let us, we have to obtain new value of XU by equating the total compressive force to the total tensile force, that is equal to 0.36 FCK BW plus 0.45 FCK BF minus of BW YF. So in this case, 0.87 FY So where YF equal to 0.15 XU plus 0.65 DF. So 0.15 XU and 0.65 DF is nothing but 80. So therefore 0.15 into XU plus 52. So 0.36 into 20, 240 mm, and XU plus 0.45 into 20, 740 minus 240, 0.15 XU plus 52. So 0.87 into 250 and 2280.79. Finally, the XU value is 109.06 mm, and XU max value is 0.53 into D. For the mild steel value, Fe 250, 0.53 into D is nothing but 400. Finally, XU max equal to 212 mm. So as we say, XU equal to XU less than or equal to XU max, and of DF less than or equal to XU. So DF divided by XU is nothing but 80 divided by 109.06 kilonewton. So 0.734, which is greater than 0.43. So MU is nothing but 0.36 XU divided by D, 1 minus of 0.42 XU divided by D, FCK BW into D square, plus of 0.45 FCK BF minus BW. YF is nothing but D minus YF divided by D. YF is 0.15 XU plus 52, 0.15, and XU is 109.6 and plus 52. So finally, YF is value is 68.36 mm. So the next one is ME equal to 0.36 into 109.06 equal to 1 minus 0.42, 109 into 400, 20 into 240, 400 mm square, plus 0.45 into 20, and 740 minus of 240, and the multiplication of 68.36, and 400 minus 68.36 over 2. So finally, we have to add the value of 66.75 plus 112.53. So next, the final value is XU equal to 179.28 kilonewton meter. So finally, you have to find out the moment of resistance value, that is 179.28 kilonewton meter. So thank you. We will see the problem in next class. Thank you.